We start.
Chapter, yeah. Okay, most of you got it correct. Let's say who was the winner? SA. So SA, could you explain who is SA? He's not here. He's a robot. Yeah. So why? So if you make a higher plateau, then you will get a shorter plateau. Okay. And that in a way is because you reach the potential sooner. Okay, you're producing more, therefore you reach the point in time at which you can produce that rate, you reach it sooner. That was just a warm-up question. Let's see. Okay. And it sounds something a bit counterintuitive, okay? But remember, we are keeping the rate of the plateau is fixed. That means what I'm draining every year is the same, remains the same. If I use 4 wells, 3 wells, 12 wells, okay? What I'm draining is the same. The difference is that, and that will come for the next question. So now here, Boyan stepped ahead. Okay, actually we have 2 correct answers. Okay, and essentially they are talking about the same. Okay, that curve, the required curve, usually when I change the number of wells, that doesn't change. Okay, we make the equilibrium all the way to the wellhead, so that might maybe sometimes change, but that's not the main reason. Okay, that pressure, if the flow remains the same, pipeline, flow line, these should be almost always more or less constant. Okay, what is changing is actually the other part of the curve. Remember, we have these 2 intersections, available and required. Okay, so the available is the one that is changing because essentially I'm making the rate smaller. Therefore, the pressure drop is smaller. Therefore, the available pressure becomes higher. Okay? Or in another way that you can think about it is that the production potential of the system increases. The intersection simply becomes at a larger rate. Okay. So let's see who is now leading. Boyan, okay. Okay, that's a trick question. So let's say, so Boyan, who's still leading. Where is Boyan? Yeah, here. Okay. So why is not, for example, the flow equilibrium of the system? So why that's not the correct answer?
Because you have a plateau rate, which is lower than potential.
Okay, there you still are at equilibrium, right, in plateau rate. The thing is that you have the choke, and the choke is causing a pressure drop. The choke is half open or 30% open, and that's flow equilibrium of the system. There you have a balance in energy. Okay, available is equal to the required. So you can have equilibrium, and that's not the potential. Fully open choke. I can have other elements in the system. If I have a compressor, for example, right, I can still operate at open choke. But if the compressor is at 20%, 30% speed, I could still produce much more, okay? And the other case, the pump operating at full speed, I could have that case, but the choke would be 80% closed, okay? So you always, to make it in a more general way, you say the maximum that my system can produce, okay? No matter how I achieve that. If it's maximum choke opening, maximum pump speed, maximum compressor speed, has to be where I achieve maximum production. Okay? And sometimes when I achieve that, I need to do some optimization, okay? We are going to talk about that hopefully by the end of the semester. Okay. Okay, who is FDL? Okay, the three of you here. You're next time we have to split you. You have to be some other things. Okay. So yeah, so the main we have mentioned this potential, right? We can calculate at any point in time. So why can we say that just take time out of the equation and we make it simply in function of cumulative production? Right? So why can we do that? Okay. Remember how we calculate this maximum rate, right? By making an equilibrium. Okay, or in the case we have just our reservoir simulator, we just put the minimum pressure there. That's how we calculate how much we can produce. When we do that, we can do that at any point. That simply depends on the reservoir pressure. Okay? And by material balance, reservoir pressure is simply a function of how much I have produced, how much I have drained from my reservoir. Okay? But in the more general sense, okay, that's for all the cases for dry gas, for example, that you have tried. But it essentially is because of the IPR. Okay? The IPR contains, it gives you the deliverability of the formation. Okay? But then you can have also a change in, if you have, on the more general case, an oil well producing gas also, okay, you can have a change in GOR, you can have a change in water cut, okay? Therefore, that's why you should, for our simple case, it's correct to say it depends only on reservoir pressure, okay? But for the most general case is that the IPR, that equation that I have characterizing how the reservoir delivers, is only a function of cumulative production, okay? Wow, that's a controversial question. Yeah?
50.
Okay, so we go maybe to quiz. If you can explain, did you have it correct?
Yeah.
Yeah. So why is it true and not false?
Why it's true, no false? You can derive it, I guess, but it's not quite sure. I will remember it and we see why.
Well, we did it for one analytical case, right? For example, for this undersaturated oil reservoir, we said, well, all the curves, all the equations are linear. And when you do that, you put both the integral and the variable in the same equation, and you solve that equation, differential equation, then you can find that is an exponential, okay? For other cases that are more, you saw it actually for this last exercise, okay? It was very non-linear. You have non-linearities in the IPR for dry gas. In the tubing equation, you have in the flow line equation, pipeline equation, everywhere. But if you plot the production potential, it should give you a fairly straight line, okay? Even though with all of these non-linearities in there, okay? And if you do that, then you see also the decline is exponential, So from that observation, you say if you have a fairly linear production potential, no matter how the equation looks like, very ugly, okay? But if you integrate that equation, it gives you an exponential decline. Okay? Actually, you can see. Wow, very different results. Okay, so how do we solve it? Okay, we have that curve, right? For finding each one of these points, we came to that production. Okay, let's say produce 5 from the reservoir. We calculate reservoir pressure, and then we run a full open choke, maximum that system can produce. Okay, that gives me that point. Now I produce a bit more, I have another reservoir pressure, make flow equilibrium, and then I calculate that point, okay, and so forth. I always have to compute for each cumulative production, for each reservoir pressure, what is the maximum the system can produce, okay? That means that the rate that I want to produce, 30 million, okay? That means when the system has produced this amount, okay, which is like 0.8, 0.9, okay? E to the 11. That's when the system can produce maximum that number, maximum. After that, if I continue producing from the system, if reservoir pressure keeps declining, okay, I won't be able to achieve any longer 30 million, okay, from that point on, okay. So just to find exactly the time, in terms of time, you have been producing that value constantly, okay, uniformly along all of those years. So you simply divide 0.9 divided by this number, that gives you the number of days that has been produced, and then to find the number of years, you divide by the number of days in a year. Okay? And I hope the number was correct. Maybe I also had a mistake, so 201 million. So what is that chart telling us? Okay, we have two wells producing to the same flow line. If I have open choke, right, both chokes are fully open, what point do I get in the chart? This one here, okay. That's the maximum. Both chokes are open. Now, how do I get the red line? Okay, you close the choke of well 2, right? Therefore, you are reducing how much the flow of rate 2. Well 1 has more space to flow on the flow line, okay, and then it starts to increase a little bit until you reach this point where you have maximum production of well 1 and no production of well 2. Okay, how do I get the blue line? Okay, you choke well 1, okay, and well 2 also has more space to flow on the flow line and is increasing slightly until you reach this point where well 1 is fully closed and well 2 is fully open. Okay, that area here, what does it tell you inside? All the feasible combination of rates. Okay, my reservoir engineer comes and tell me this combination should be feasible, this combination should be feasible, any combination that falls inside. Okay, because I can achieve any of these points bar choking. I don't know how much. Okay, for that I need my choke model, but I can achieve, I know I can achieve them by choke. Everything that is outside, not feasible. I cannot produce. I have to correct the rate. Okay, so we have in our case was 200,000 and 1 million, so it's someplace here. It's barely non-feasible. Okay, so you should reduce maybe a bit the rate of well 2 to bring it back. Okay. So one thing, why you see here you have a small jump, right? The feasible area, the non-feasible area, and you have a small jump. Why do we have this small jump? Okay, simply comes from the equation. When you have the flow rate of 1 starts to be too small, okay, simply you have a discontinuity. Simply you are not able to find a solution for those low rates. Okay, simply means effectively the well will close when you reach a certain low number. Okay, that happens for some systems when you're solving the system of equations. So be aware of that. Okay, so let's see who was the final winner. Okay, Buyan, Sage, and J.A. I don't have any prizes today, so sorry for that. Okay, so now for the second part, you're going to get an exercise. You should work in groups of, I would say, on 3. Okay. But first I want to say, just, so first we took a recap Kahoot quiz. Okay. And I just want to clarify also something that people were a bit confused by exercise problem 2 of exercise set 1. Okay. You got an equation that was simply the Q production potential of the field, okay, that was equal to the number of wells times minus M GP plus Q PPO. Okay, and you got some numbers for here and here.
This exercise set 2, right?
Hmm?
Exercise set 2.
Yeah, set 2. That's correct. Okay, so that number, okay, in theory you should have to do the way you did it for exercise 1 and exercise 2. Okay, for problem 1, exercise 1, problem 1, exercise 2. You simply have to make flow equilibrium calculations. Okay, calculations if you have the production system model, okay, if you have the well model, if you have the network model, if well model and network model, okay, Or the other option is you use simply, if you're using a reservoir simulator, you just impose the minimum flowing bottom hole pressure, okay? Impose PWF min for if reservoir simulator only. In this case, what I'm doing, I'm simplifying your life, okay? I'm just saying, don't do any of that, okay? I have done it beforehand for you, and I just give you an expression of this potential, of this maximum rate versus cumulative production, okay? I'm just simplifying your life. You don't have to make flow equilibrium. I have made it already for you, okay? I went and I ran for a lot of PR, okay? I came and I ran this equation and I find how much was that potential rate. Okay. When you are in the for the plateau period, simply the rate of the field will be constant. Okay. And you can find the end of the plateau. You already know how to do it, right? So you have here GP. Okay, simply you go, just the exercise we have made here. Okay. Now for subsequent times, you know you're going to be on the line. Okay, but you so one way to calculate that I suggested to some of you is to take GP. You know that GP at any position I will be GP from the previous time step plus, if you're using the trapezoidal rule, 0.5 QI plus QI minus 1 times TI minus TI minus 1. Okay, so you have by the end of the plateau, and you start exactly at the end of the plateau. Okay, you have made time and Q of the field. You have made your plot like that until TP, and then you want to find out what will be the rate here QI at this time. Okay, TI. So you start. You have Q from the previous. That for this case will be the plateau. So you have this guy. You have the time that you made the step. Okay, you decide. You're doing your calculations every year. You're doing your calculations every month. You have how much has been produced in GP minus 1. Okay, you have this number here, the GP. But now you want to find out these two, okay? But you have, on top of that, you have another equation, which is a potential equation. You know, because you are in this area now, you have to be producing always at the maximum. And you know that for that, the maximum is the Q of the field should be equal to the number of wells times minus M GP plus Q PPO. All of these are given. This is given, this is given, this is given. Okay, and here you have one more equation that you can apply for that point where QI is NW minus MGPI. And you can go and solve that system of equation. Here you have one equation, here you have another equation, and you solve those at the same time, simultaneously. Okay. Now there is another way you can do it. Okay, and you can use exactly the same approach we have used for in the problem 1 of exercise set 1. Okay, you have time. Okay, at some point you have T plateau, and then you have TI. So you can compute the GP. First you have the rate, right? And for all of these, you will have the plateau. Plateau, plateau, until here. Now you have the GP. Okay? And for GP, for time I, you can come and say, you can calculate, okay, assuming that you have been producing the previous, so it will be your previous plus Q plateau times TI minus TP. Okay? You are assuming that you are producing that throughout the year with the rectangle rule, okay, from the end of the plateau. Even though you are sure it's not so correct because now your rate will be less, okay, but it's just an approximation. You're assuming it will remain constant. Okay. With this GP, you're also able to calculate the Q production potential of the field. And you had one column. Okay, for that you use this equation. This equation will be here. So for 0 GP, you calculate some QPP of the field until you reach a point, right? So when you apply it exactly for this time, what's going to happen? Your plateau rate will be below this potential, okay? So therefore, you should use now, in this time, that potential. Okay, then you move to the next time step, Ti plus 1. And now again, you don't have the rate. You assume you are producing that rate constantly throughout the previous year, all through the year. With that, you calculate GP. GP, you calculate your potential, okay? And that's the rate you're going to use for the next time. So it's exactly the same. You don't have to come and solve this system of equation, okay? You can just assume that calculation, flow equilibrium, that calculation applying the minimum bottom hole pressure, okay, simply comes by this equation. I don't have to solve anything, I just apply that equation. Okay. Okay. With that clarification, we come to the second part of the class. Okay, we are going to make an exercise, which is published on my website. Well, you're going to make an exercise. I'm going to help you a bit. And that exercise is part of exercise set 3. So it's so we have here is like it's a very complex problem. Okay, here we're including. It has a part on boosting. It has a part on flow equilibrium calculations. It has a network. Okay, and it's also in time. So it has all the things we have covered so far in the same problem. Okay, so we have to take one step at a time. What we are looking here is Gullfaks South field. Okay, you have two templates, M and L. You have also some other template called N. Okay, we are neglecting that template for now. That we say the production is very, very small, so we neglect it. Okay, such that we can solve it with Excel. We have two templates. They produce with each one has a flow line, goes to a something called a tau head. Okay, which is like here. You have two templates. One has 3 wells, one had 4 wells. Go to a tau head, and then from there you have 2 parallel lines going to this gravity-based structure, Gullfaks C, where it is processed. And the thing is that these 2 wells were originally oil wells. But with time, simply the GOR starts to increase, you're producing too much gas, and they decided to convert it basically to a gas wells, to gas with some liquid. So if you see here the cross section, you have 2 units, they are split by a fault, and they simply, initially the wells were completed in the oil layer, and they recompleted a bit higher on the gas layer. And you will start your calculations from there. You have the volume of the gas that you have, the gas cap you have in place, and each wells are draining from different units, okay? Even though it's a very complicated unit, we say these are 2 reservoirs, okay? 2 containers. And you have to basically, the main task is to compute what we are computing all the time, which is production profile. Okay, you can use the same equations, dry gas, material balance. This is all the data. Now you have two reservoirs. So you have to take the volume of each reservoir. You have to take the number of days producing per each reservoir. You have a different number of wells per each reservoir, in different initial pressure, different seed, tubing, flow line, etc. Okay, so now essentially you have a network that you have to solve. Okay, so you have to perform the field after that point where the wells are recompleted. You want to produce with a rate of 10 million in plateau, and you just want to predict for how long you will have that plateau, and you want to predict also the post-plateau behavior until the rate is 2 million. That's the minimum economical rate. Okay. Now, there are a few things, so you can go and read. I suggest you have groups of 3, and then you work on the exercise, and I can help you as needed. Okay, but you have basically, if we make a simple sketch of our system, you have here a flow line. I don't need to simulate both, okay? Both are going to be exactly identical, but I can say I have a flow line that is carrying half the rate of the field. Because if both of them are identical, there is no point really to waste one equation on that. I know exactly the conditions will be exactly the same. So here I have P tau head, and then I have 2 templates, okay, that now the rate won't be the same. Now I have Q of L and Q of M, and that I have to find how much is that. Okay, and then after that I have 4 wells, I think, in L, and 3 wells. And here we're going to make the assumption that wells are identical within a template. That means that the rate that I have on one well will be QL divided by 4, and this will be QM divided by 3. Just to make, to not solve too many networks, okay? Here our main thing we want to calculate is how much is the splitting between these 2 units and how they're going to deplete in time. Okay, so we don't know yet. If you see here, we don't know how much we're going to produce from every unit. Okay, we don't know how much you're producing from each reservoir. It's empty. So I suggest you here that you use, first you run an open choke simulation. Okay. The plateau production of each template, you have to run an open choke simulation. Okay, it should give you a value much higher than 10, maybe 20, something like that. Okay, you will see how much each template is producing in that case. Maybe one template will be 12, the other will be 8. Okay, and then you calculate a split factor for each template, for each reservoir. Okay, that you say the Q that you calculate, let's say 12 divided by 20, okay, the 8 divided by 20. So you calculate a factor for each one of them. So to estimate how much each reservoir unit should produce in plateau rate, and that's something the field designer makes often. Okay, they make the decision based on the potential. Okay, one often uses the potential. Okay, so I calculate at time 0, okay, when I haven't produced anything, well, any gas, okay, I have been producing that reservoir for a long time, but I don't produce any gas. At time 0, run a flow equilibrium calculation with open choke. Okay, and then I'm going to calculate Q production potential of the template L. I'm going to calculate the production potential of template M, and then I will calculate the production potential of the field. which, if I want to produce 10, should be much larger, okay, than 10. And then I calculate split factors. The second step, that's the first step. The second step is calculate split factor, production split factor. Where I say for L simply will be QPPL divided by QPP of the field, and for the M will be QPPM divided by QPP of the field. Okay? And I'm going to get a factor. Let's say according to that size, according to the productivity of each template, one will be 30, the other will be 70%. So the third step is to calculate plateau or production split at plateau rate. Okay? And that will be Q plateau of L will be simply the Q plateau desired of the field times this FL, and the Q plateau M will be the Q plateau of the field times FM. Okay? And I use that. If I produce at open choke, no restriction, I'm going to get that splitting. So I'm going to use the same splitting for when producing in plateau range. So that's how you're going to find out how much each template is producing initially. Okay. So another suggestion is, remember what we have done one of the previous lectures. I don't know which one was it. Yeah. And we're going to talk a bit later about that, but why is that? Why do we use this very strange way of splitting? Okay? The idea is that you split according to what each system can deliver. Okay? So, and that the intention is that they reach the end of the plateau more or less at the same time. If you produce too much from one that cannot produce too much compared to the other, okay, that will reach the end of the plateau sooner. So that's, we're going to go more, you're going to get an exercise on field planning scheduling, okay, with two fields. But for now, think that this is like you have these measures, these fraction measures is like the capability that each one can produce, okay? So you split according to the capability. If one that cannot produce more, you give it the high task, it's going to get burned very quickly, okay? It's going to get tired very quickly. So you share it. It's like you have a big guy with a lot of muscles, you have a very skinny guy, and both of them has to carry the same number of bricks, okay? One of them eventually is going to fall down, the skinny one maybe, okay? So you're saying, with that you're saying how strong each one is, and then giving rates based on that. Okay, if you want to think it in a very simplistic way. And now we go to this, so remember, to solve this problem, you think about network, you get scared, okay, I have to solve a system of equation, but remember this very important lecture, okay? If we are in plateau rate, if the delta P of the choke is positive, I simply have to come and calculate with the rate, calculate the pressure, wellhead pressure of template L. With the rate, I simply calculate the wellhead pressure of template M. And with the rate, I calculate the tau head pressure, and then I calculate the template, the required and the available, the wellhead and the available, and I compare. Okay? If one is greater than the other, that means I can produce the rate. I don't have to do anything else. I have verified that I have more energy than what I need. The problem comes, I have to run equilibrium if it's not. Okay, if I have less energy than what I need. So for that you got an Excel sheet that you're going to use, and it's very similar to the one for Snow White. Okay. But now you have a bunch, you have two reservoirs, okay? So you have the rate of the template, the rate of the well on that reservoir, on that, you have the GP, how much you have produced from that reservoir, the recovery factor from that reservoir, the C of that reservoir, reservoir pressure, okay? So from here, with that rate, you fix it. You know how much it is. Okay, let's say is initially 6. You have reservoir pressure, you calculate bottom hole pressure, and then you calculate wellhead pressure. You stop. Okay? Now, this you don't know yet. Okay, that's the available, and this will be the required. This one I calculate from the reservoir. This one I have to calculate from the separator. Okay. Now I go for the second. M. I have again all the things for M. I go reservoir pressure to bottom hole pressure to wellhead pressure, and I stop. Okay. And now, it's a bit long Excel sheet. You have the plateau rate, right? You have the plateau rate of the field, which should be the sum of the other two. Let's say 6 plus 4. So now you have P separator, and you counter current. You calculate the required pressure at the tau head. Remember, with half the rate. And from the tau head, you move also counter current to the template, to each one of them, to template M and template L. And with those two values, you can compute the delta P of the choke in L and in M. If positive, no network, nothing. You continue to the next time step. If negative, you're in trouble. Okay. So for that, you have this other sheet, which is to calculate flow equilibrium. When you need to calculate flow equilibrium, you have to substitute your reservoir pressure here, and then you have to change. Remember what we discussed? We usually prefer to change bottom hole pressure until you find equilibrium. Okay? So not to confuse you anymore, I suggest you start by, getting in groups and reading a bit closely the exercise, and then we take, maybe after 20 minutes or 30 minutes, we take another joint session if you have any question. Okay? So let's do that. Let's do that now. You go to File, Options, on Formulas, okay? You have to be sure that it's set to automatic, because I think some of you might have manual calculation. That means that every time you change a value in the Excel sheet, okay, it's not going to recalculate automatically. That is, if you have a very heavy Excel spreadsheet with many calculations, then people usually prefer to do it manually. They press F9 and then everything gets calculated. So for you, just change it to automatic, okay? Therefore, you... Okay?
Now it's changing. Now it changes.
Now the air...
Automatic is good.
Because it's just right now. I should use this that this problem is very interesting. Okay, it's supposed to to make you think. That's the intention. Okay, but remember, what did we say for solving networks? Okay, you can have many different methods. Okay, you can use all kind of methods you want. But so what we are doing here, okay, we have a choke. Remember, the choke is per well. We don't have a choke per template. The choke actually is per well. And then all of them go to a common point. We have 4, okay, in the case of template L. Here we have to a common point called P template of L. Then that goes with a flow line to a point called P tau head. And then I have these 2 lines that I can just look at one, okay, with QF divided by 2. And then I have the same thing, P. I have a point here, P template M. And then I have these 3 wells. Each one of them has a choke. Okay. So what you have to define first is an equilibrium point. That's the first thing you have to do when you look at that network. You say, I want to solve it, and I have to define an equilibrium point. Okay. As I mentioned, this is very similar to the 2-well case that we have done in class before. Okay, you have two guys producing to a common point. Okay, and if this choke was closed or had some delta P, that creates a problem, right? But they are fully open. We are running a simulation with fully open choke. Therefore, this is exactly the same as that case. So I decide to use this point as my equilibrium point. And with any equilibrium, I say I have to get to that point from all the bounds. Okay? So I go from the separator all the way here. Okay? From the downstream bound all the way here. For that I have to use this equation, line P1. Okay? I have P2 here, and I want to calculate P1. Okay. Then you move from reservoir pressure, bottom hole pressure, you move wellhead pressure, and the choke is open. So there is no pressure drop. You can continue all the way here. Here I have to use the rate of one well in M. Here I have to use the rate of the template, M, until I reach that point. So I move bottom hole, wellhead, and then wellhead junction, tau head. Okay? So I do that from M, from L. Okay? For this one I have to use IPR, I have to use TPR, and I have to use flow line, FPR. And all of them I want to calculate to the condition downstream. I'm moving with the flow. Okay? Now, what do I have to change, okay, in each one of these two? Okay, if you see very roughly, I have to change a rate, okay, and a rate here, such that these 2 rates, they give me, all of them are the same pressure. If I fix that rate, I'm able to calculate that pressure from this side. If I fix this rate, I can calculate the pressure from this side, and with these 2 rates, I can calculate the pressure counter current. Okay, so I don't need anything else. I need to assume the rate and then change these rates until these 3 numbers are the same. That's how we start the problem. Define the equilibrium point and then define what do I have to change to achieve what. Now we go to the sheet, okay? And here I'm going to erase, and I'm going to try to solve it very quickly. Okay. And here we say, I told you, the solver is using like a Newton-Raphson type method, okay, to find the solution. So you can give it either the rate, okay, but the rate you have a problem. If you have an overshoot, let's say assuming a very high rate, you will have the square root of that quantity. So you're going to get a value error. Okay, so that's why I suggest you start with bottom hole pressure. And we start with the bottom hole pressure very close to reservoir pressure, 220, and let's say 200. Okay. Then we move from that point. We have bottom hole pressure. We calculate the rate, with the IPR equation from each well. Okay, here we're talking on a well level. Okay, IPR Q, and that will be C N PR and PWF. That will be for template L, for a well in template L, and that's for a well in template M. After I do that, I still move on the well, so I still have to use the rate of the well, but I move all the way to the wellhead for both. So for that I use tubing. Which equation of tubing I use? I have the pressure at the bottom of the tubing. I have to calculate the pressure at the top of the tubing. Wellhead, P2. CT, S, P1, and Q. Okay. Delta P choke, I say initially to calculate this splitting is 0. So I just simply put 0, 0. And the template, which is the pressure downstream the choke, simply will be this minus that. Okay. Sorry, this minus choke. This minus choke. Exactly the same number. Now be careful, I have to change now. Now I'm moving on a conduit. I have to move from here to here, right? But this conduit has the whole flow rate of all wells, of these wells that I have here, 4. So that's why I have, before anything else, I have to calculate the rate of the template, which is the rate of a well times the number of wells per template. Okay. And then I need to move once more to the towhead. So I have line P1 and I want to calculate P2. So I move from here to here with the rate of the template. Line P2, the flow, the pressure, and then the rate. Finish. That's where I stop. That's my equilibrium point that I define. I stop there. Okay. Now I have to come from this point. I have to go back and calculate the last part of the puzzle. For that I need the rate of the field divided by 2. Okay. So I come here. The rate of the field is the sum of these two guys. And then the pressure will be line P1, the flow, the resistance coefficient of one flow line. Remember, I have two parallel. Pressure 2 is the pressure at the separator, and the rate is this rate divided by 2. Be careful. Okay? You see they are very different. The numbers that I assume, 220, 200, tells you that there is more pressure than what I really need. Okay? What should happen intuitively? This number has to go down, right? And this number has to go up. How does that number goes down? By flowing more, right? If I have more pressure drop, the rate is higher, then I have more pressure drop from here to here, from here to here, from here to here. So the rate has to go up. Okay? And this one, how does it go down? Again, by increasing the rate. How does it go up? Increasing the rate. If I have a higher rate, then I will need a higher pressure to flow against separator. Okay? So a trick I told you, you can use any trick you want, but I say, you can say, to make all of them the same, I calculate the average, and then I calculate an error that is the value minus the average, and I block the average, and I square that, because I'm going to sum it with all the others, and I don't want it to be positive or negative. So I just want it to be positive. Then the sum of all of them will be that. And that's one cell where I can use a solver. Okay? Only one cell. Solver cannot apply on many cells. Just one cell. Okay, so if I drive this to 0, all of them are going to be the same by changing these two pressures. Okay, solving that, minimize is the same, it's always positive, so minimize is equal to 0 by changing these two pressures. And I also try to give some help to the solver. Don't try pressures higher than reservoir pressure, then you are going to be injecting. Okay, so just try keep it lower. Okay, let me just, this one, actually this one should be less than this one. Okay, we found the problem, and the problem is in well number in L. Okay, so I just try, remember Newton-Raphson depends on the initial seed. If I for some reason shoot too long or shoot too short, I might find a place where the function is undefined. Okay, so what I try, I say this rate was too high, you see. The pressure I have here is not enough to reach the wellhead. This rate that I'm taking here, 4 million, is just too high. I never reach the wellhead. So I solve that by simply increasing a bit the bottom hole pressure.
Could you add a lower constraint as well? If
Also.
If you take the pressure in the separator and calculate what rate or what pressure you need at the...
You can put all kind of heuristics, but it's not so simple. You have to give it some thinking. Okay.
If you take the separator pressure and calculate all the way back to the DHP.
The thing is that you don't have the rate to calculate that pressure. Okay. So, but you can use any. Okay, and you can put any heuristic to try to help the solving process, such that to help, don't try these numbers, this too high, this too low. But at the end, if you want to make it fast, just do some trial and error. Okay. Okay, so here we found the solution. We found the rate per each template, which is 14 million, 15 million by template L, and 7 million. That gives you 22. I just need to produce 10. Okay, so I calculate now that fraction, that split fraction for L. That will be this number divided by this number. And I calculate a split fraction for M. That will be 0.6, 0.7, and the other number will be 0.3. So that tells me from the 10 million, 7 million has to be produced by template L, and 3.2 million has to be produced by template M. Okay. Now you have these two. You know how much is that? So it's this is 6.7 e to the 6, and the other will be simply the difference. Okay, Q of the field is 10 million, and the Q of template M will be the difference between this guy and that guy. Hmm? Yeah, sorry?
But now you're at potential, right? You're not at plateau.
No, I'm at plateau. I remember, if I was at potential, I will be producing 22. Okay? I don't want to produce 22. I want to produce 10, much lower than that, much lower than my potential. For that, I will have to choke.
So you use the split factor at the initial.
You use the split factor calculated at potential to split the production during plateau period. And we will see later on more detail that, but what I told you, this indicator tells you how strong one template is compared to the other. Okay, this tells you that this one is 70% or is stronger than this one. Therefore, it should produce more in the plateau.
Does the split factor not change as you produce?
Yeah, that's a more advanced calculation. We are assuming here it's constant, but it will change. It's better if you change that factor for every time step.
Because what if you had both wells going as plateau, going at potential until they reach the plateau, like the field plateau?
Mm-hmm.
Because if both of the
if they
are at potential, then you would get the speed potential, right? So
if both go at potential, you really cannot do much. Okay, the potential is simply if they are going to follow one decline line. you cannot really control that decline. But if you are able to choke, then you're able to control how they will decline. Okay?
So you would want to find the split factor at the field potential.
I found the split factor at the initial state of the field. Okay? What I could do, which is something I'm not adding here to lower the complexity, you should at every time step make this calculation. Okay? For the next, let's say for number 1, you found the splitting. You say 33 million here, 7 million here. Then for the next time, you calculate another splitting and you see if that changed or not. Okay? But that's more advanced. Here we're going to keep it constant here in class. Okay? But that's how some reservoir simulators, some simulators use that logic. Okay, they use the potential. They have to run a full open choke simulation to see how much each well will produce. Okay, we are keeping things simple for now. So simple, you find the splitting initially and you use that for the rest of the plateau. Okay, then after you have that rate, we should put it in red. Okay, you can go and do calculations on the rest of the system. Okay, you can find out what is the pressure, available wellhead pressure. You can find the required. Here, remember, we are changing the equilibrium point. When we make that calculation in plateau, this one will be different than 0, and this one also. So what we are doing here, we are putting the equilibrium points here, right? We have this rate, we have this rate, we can go all the way from here to here, and from here to here. We calculate that pressure. And then we go from here to here, and here to here, calculate that pressure, and then we compare. This one is bigger than this one, I can produce the rate. If not, I have to use that again. Okay? So let's do that tomorrow. Let's close the class for today. And let's continue tomorrow a bit with the exercise. Before we close, any other question? No? Okay.